Hi everybody, we're at equilibrium at the spring. There's no force being added right now. And as here, you can see with the pedometer, we're adding 1 Newton. And as you get closer, you can see that the spring rolled down to 24 centimeters. Now, if we keep going here, we go down to two newtons. Our spring is now at 31 centimeters. And then we go down to 3 newtons, about 3 newtons. We are now at 37 centimeters. And we go to 4 newtons. Oh wow! Okay, my hands in the way. We go down 4 newtons. We get to about 43 and a half centimeters. And then if we were going to down to 5, we go down 5 here, 5 newtons. We are at about 50 centimeters.
About 50.
About 50 centimeters.
Yeah, about 50.
Okay.
Okay, so in this 5-spring system, these springs in parallel on top begin at roughly 13 centimeters, and these springs at the bottom begin at around 29 centimeters. And when we add 150 grams, the top springs shift about 3 centimeters, and the bottom springs shift around 8 centimeters.
For our K constant, what we did was use the ending position, the ending distance, subtracted from the starting distance. So once we did that, we got 34, and we had to convert that 34 centimeters into meters. So we did that by dividing by 100. So we got 0.34 as our x, or our distance, and then we isolated for K, found our K constant by dividing 5 newtons, which is how much we applied to find 50 centimeters, and we divided by 0.34, which is the distance in meters, and our theoretical K constant is 14.7. And then now as we go down here, we see, and then when we use our system, we measured that the system on the upper bound moved 3 centimeters down, while the bottom moved 8 centimeters down. We then converted it to meters, centimeters to meters, so we get 0.03 and 0.08 as a distance. And then we got 1.47 because that was the amount of weight we applied to the system. That's the amount of weight we applied to the system. And 1.47 because we had 150 grams applied to it. We converted that to kilograms, and we times 9.8 to find the force acting on it. So we divided the same thing as we did before. We did 1.47, the force, divided by the distance, and we did it first for the upper bound, which is 0.03, that we get 49 for our K actual value for the upper bound, and then we got 18.375 for our actual K constant for the lower bound.
Our theoretical K constant was 14.71, and our actual K constant that we found was 18.375. And there's a slight discrepancy between them, which could be caused by the slight leaning in our system. But for the most part, they are the same.